then I need to. Okay. So let's get started. Before getting into the content, let's review a little bit what we have learned so far. I think maybe I should turn off the light. It's better. Is it better? Okay, cosmological exact solution today I will cover more in detail. But anyway, so we have this F Freeman-Lemaître Robertson-Dyson equations. So if you can have this Haber-Romator law. But before that, we learned the Kerr-Black hole. And curve metric is given here, and the important part is this GT phi. Unfortunately, resolution is not good. So this will give you some rotation. And then when the horizon will appear when this delta equals to 0, And so this is the outer horizon, this is the inner horizon. Unfortunately, resolution is not that good. But anyway, let me move on. So one can just move from the, how to say? This is called BL coordinate. I forgot the, huh? Yeah. I don't know how to pronounce it anyway, so he can pronounce it. And then from BL coordinate to Cauchy coordinate, you need to change this kind of variable. And then you will encounter that ring singularity. Yeah, this is from the Cauchy coordinate, Cartesian one, and when r goes to infinity limit, the behavior it become like this way. So the stay far from the black hole, the metric become like this way. Okay, and then. So we have a frame tracking. So even though so there is no how to say rotation measured at infinity, if you go into close to the black hole horizon, you definitely have you are forced to have an angular velocity. So this is schematic diagram for the frame tracking. Okay, frame tracking. And the feature of black hole, which is stationary, which means that the metric is independent of time. The axis symmetric means that the metric does not depend explicitly on phi, except no phi, and it's not static. Means the t goes minus t. If you take t goes minus t, there is a term like d phi dt. Sorry, d phi. And dt, there is a term like this way. This will make the metric not invariant under this time reversal, so therefore it's not static. And it's invariant under simultaneous change t and t goes to minus t and phi goes to minus phi is expected from the anyway. So that's the and it's a asymptotic flat. Okay. And then we can use this kind of like how to say Eddington-Finkelstein coordinate, and to resolve the apparent singularity at the horizon. So then Kerr singularity occurs when this equation is satisfied. Okay. So therefore, rings you can encounter, witness the ring singularity. Okay. So when r equals to 0 and theta equal to pi over 2, you encounter ring singularity. So this is a diagram so kind of like a spherical coordinate in the co-geometry. So this is outer horizon and inner horizon. Inside you have a ring singularity here, and you have the kind of like a cross time-like curve. The CTC means cross time-like curve near the ring singularity. So that's what's happening in the co-geometry.
Where's the inner pink line? There is the ergosphere outside. What's the pink region inside?
This one?
No, this is the ergosphere.
Ergosphere, yes.
But the pink dashed line inside.
It is in the horizon.
Inside that.
This one?
Yeah.
This one, I don't know. I don't know, to be honest. Pink dash line, I don't know, to be honest.
When you solve the GTT equals to 0, you will get this line also, but it does not have physical interpretation.
I see. So, yeah, GTT equals 0 is this pink line outside, but inside there is this exist. I see. Thank you very much. Okay, so this is the causal structure of the curve singularity. Okay, and then yeah. So here, yeah, RP is the outer horizon. This is RM is the inner horizon. Here, outer sphere, and so on. Okay, this is the causal structure. As you can easily, this kind of like a Eddington Finkelstein coordinate in curved spacetime. Here, outer horizon and the inner horizon. Again, the light cone is the moving toward the R is smaller region. Okay, and then you have ergosphere is characterized by GTT. A surface ergosphere is characterized by GTT equals 0, and which is outside of the outer horizon. So in between is called ergosphere. And this is a rough picture of the. And here, the surface of the ergosphere is called stationary limit because the angular velocity becomes 0. Okay. So if a particle initially falls radially with no angular momentum, from infinity it gains angular momentum during infall, and angular velocity are seen from a distance. So this is the really angular velocity frame dragging effect. So as I mentioned, so here, so if the direction of black hole spin, but if it's a co-rotating is yellow one, and counter-rotating is this kind of blue one, and around the surface of our sphere, it's a force to drag to the co-rotating. So that's the dragging of inertial frames, or length Stirling effect. Yeah, so the curved black hole, so the typical feature of this curved black hole is that from ergosphere one can extract the energy. One process we learn is called Penrose process. We learn if particle splits inside our ergosphere, one particle can have a kind of negative energy observed from infinity, measured to infinity. On the other hand, the other one has the positive energy and angular momentum, so that you can extract energy. The other process, famous process called Blandford Znagic process. Anyway, so this is another process which kind of use electromagnetic effect to extract energy, which I'm not going to go into detail. I mean, I can cite some reference for this one, but I'm not going to go into detail. But essentially, the idea is the same. So the Penrose process, as I mentioned, is that but this is kind of not the correct diagram, but so if you have the co-rotating, counter-rotating one enter the Algol sphere, one particle can have a negative energy, and then so that one can exert so mass, energy, and momentum, angular momentum. So since the first one is the counter-rotating and to enter, and then how to say, the particle 2 has the positive energy and also the co-rotating angular momentum with the black hole. So therefore one can extract even angular momentum. So that's the point. Okay, so when A is equal to M, so this is a physical one. No? Yeah, I think physical one. And this is a Penrose diagram for the curved black hole. For maximally extended one, or eternal curved black hole, is like this way. And also we encounter the time-like cross curve, so which is the somehow appear as a solution of the Einstein equation, but it is believed that in reality there is no such a thing occur. So there's something strange happening even in the solution in the Einstein equation. Okay, so this is a rough picture of the cross time curve. Okay. So these are, we haven't talked about this one. Okay. And we also learned the kind of Leissner-Nordstrom black hole, which is static one, but with the charges. Okay, so it has an electromagnetic field, and the solution is given like this way. Okay, and then you have an inner and outer horizon again. So this is the plus minus means outer and inner horizon. And when the RG is equal to Q is the extremal solution, so which has which the outer and the inner horizon. So this part becomes 0. So therefore, outer and the inner horizon coincide for this kind of extremal case. And then I don't understand, right? Leissner-Nordstrom black hole can be more compact than anyway. And then when if charge is the greater than the mass, then in fact this is the horizon becoming, and the position of horizon become imaginary. So therefore you encounter negative singularity. So it is believed that it's not physical solution. Okay, so this is the causal structure. It's very similar to the what we saw for Kerr. You have an outer and inner horizon, and then you have causal structure like this way. Okay, so that's the case. Okay, so this is schematic figure for the Leissner-Nordstrom black hole. So because it's static, so there is no flat frame dragging effect. No, it's not static. Static, it's okay. It's static. So you have an outer inner horizon. It becomes like this. Okay, and then so this is a physical diagram for the Penrose diagram for Leissner-Nordstrom black hole. Yeah. And this is maximum extended one, or eternal Leissner-Nordstrom black hole. Yeah, I think I should mention it's a maximum extended one. Okay, and then these are I think geodesics of geodesic motion around the Leissner-Nordstrom black hole, which I haven't talked about it. And then so in the homework due in few days, on Sunday you have to solve the Einstein equation for Kuhn-Newman black hole, which has angular momentum and also charges. Okay, you can have charges. The metric is the same, almost same as the curve, but there's a way to incorporate the charges in the delta. And there's some q squared here, and so on. So there's a way to incorporate the charges in delta, and yeah. And here is the upper one is the outer position, outer horizon. A is the, what was that? I think electromagnetic, how to say, the gauge field, and so on.
Area.
Oh, sorry, area, sorry. Area of the outer horizon, okay. And the Kerr-Newman metric represents the simplest, stationary axis symmetric asymptotical flat solution of the Einstein equation in the presence of electromagnetic field in 4 dimensions. Okay, so that's the case. Okay, and then yeah, it also have an Auger sphere. In fact, one can solve in the presence of the electric field. You can add this term. You can add this term. Okay. So it's almost same as what we have learned so far. So this is the electromagnetic field from black hole, coming from black hole. Okay. So the solid line is the electric field. Dashed line is magnetic field, like this way. Okay, and then so what's this? I don't understand this figure. Anyway. Okay, field around the ring CRT. Okay, so these are the Kerr-Newman. Anyway. Okay. So these are, okay, what we have learned. Okay. I think let's finish that, the sharing the slide. And then move on to the content of the Okay, so last time I had a poor job of cosmological. Exact solution. And then one is FLRW we are talking about. So this is homogeneous isotropic. So this means no special point. Shell point in the universe, and then no special direction. Okay, so that's the meaning. Okay, so the no special point means that if you do the translation of the space-time, the physics observed here should be the same as physics observed here. So that's what it means. Okay, and the isotropic is the physics look like whatever. What's happening if you look at this direction, this should be same as looking at this direction. There is no way to distinguish that. So that's what it means. Okay, so so that's isotropic, and then these two, sorry. So these two will compose so-called cosmological principle. So this is cosmological principle. Principle. These two conditions is called, and this one is supported by so-called how to say CMB cosmic microwave background. Okay, cosmic microwave background, and then. Yeah, microwave background is perfectly, I mean, not completely perfect, but almost perfect. And there is smaller deviation coming from whatever, like inflation and so on. That's, I'm not the expert on it, but anyway, so long time ago I also learned this kind of stuff. But anyway, so this was supported by this CMB experiment. And if you look at I also add the figure in the lecture note. If you look at this figure, it's almost homogeneous isotropic. Okay. And then, so to do that, so we need to, so the space metric should obey. So RJKL. So this is 3-version space, means the 3-dimensional space-time should obey something like this one, some constant, which is constant ik gjl minus gil gjk. So like this way. So like this way. Then the metric is like this way, should be written like this way. So A square Iij dxi dxj. So gamma ij is the space part of the metric, with A square is a scale, and then dr square 1 minus kr square. Like this way. And once you change the variable, r introduce so-called chi variable, r is equal to square root minus k. A square d chi square plus sine square chi d omega 2 square. Or you have the same thing, A square d chi square. Okay, so this is a 3-sphere, S3, and R3, almost locally R3. And then A square is equal to d chi square plus sinh square chi d omega 2 square. And this is hyperbolic. Locally, hyperbolic 3-dimensional surface. So these are the essentially solution for the metric which satisfy this one. This is k equal to positive, k equal to negative 0, and k is negative. So that's the case. And then we have, so space-time metric is something like this one. Like this one. So this can be understood as the size of the universe. And if we solve the Einstein equation with the I mean
Those particular
yes.
ones are for k equal to 1, 0, and minus 1. What right? There's 3 options.
K.
Therefore, fixed k equals 1, 0, and minus 1.
Yeah. I mean, you can scale. you can scale chi and so on, but you can just make it positive or negative, but it's not essential important anyway. Okay. And then so we assume that the universe is filled a perfect fluid, so therefore the stress energy tensor will be like this way, G mu nu. And locally it can be written rho PPP in the case of last spacetime. Okay. So locally flat metric so it behaves like this. And we'll solve the Einstein equation, G mu nu. And the last time the quotient was wrong. That's why I got confused last time. Yeah, so now I just solved the mathematical again. Now I understand where the mistake lies. Lambda G mu nu. Okay. And then what I made a mistake is that R00 was okay actually. R00 was okay. -3 A double dot over A plus A dot like this way. So there was some meaningless quotient 3 last time. That's why I got confused. Anyway, so the previous time, so there was a 3, but now correct. This is a correct curvature. Okay, correct curvature, and R is equal to 6 times A double dot A plus. This way. So those are the essential information, and then we can just write down the G00 is the 3 times A double dot A square plus K over A square, and then Gij is equal to -2 A double dot over A plus A dot over A square plus K A square, and then 3 Gij. So this is the left-hand side of the Einstein equation, and now we can evaluate right-hand side and make it. And evaluate the right-hand side, and then consequently, we get the Einstein equation for this homogeneous isotropic universe, and which is something like this one: K over A square Okay, so this is the 0, component of the Einstein equation, 0, component, and this I component, ion component. You get this one. And then these are called Freeman equation. Freeman equation, and we can just plug this one into here, because I mean this part. So this part the same as this part, so one can eliminate this first derivative of A, and then what you get is the A double dot over A is equal to minus 4 pi like this one. Okay. So if you plug this one into here to eliminate a dot, so you get this one, a double dot, and so on. Okay. And this is positive, and this is positive. Okay. So that, and this here, to get this accelerating universe, a double dot is the positive, lambda has to be positive. Okay. So that's the case. So this means that the accelerating universe so lambda needs to be positive. So that's the case. Okay, so that's the case. If the right hand side is negative, a double dot is the negative, so which means decelerating. Okay, and decelerating. And then from here one can derive Hubble law. So the distance, so there's a, how to say, the observer O, and then there is something happen in the universe. There's some star. Star is here, and distance between here can be understood as essentially A times T chi. Okay. So the length is like this way. So therefore, as time goes by, how this how to say length will change? You just take the derivative. So this A T chi. So this is distance. Okay, dt. So velocity is the how to say d dot, which is a dot, t chi, which is a dot, a d. Okay, so that's the case. So therefore, once you set this is equal to t is equal to t current time, so the velocity of the star is proportional to the proportional distance. Okay. So that's the, so in the lecture is, I call it Hubble Lemaître law. Okay, Hubble Lemaître law. And then, yeah, so that's the, okay, so that's the case, and this is called H naught. Okay, and you can plug this one into the upstairs, and what we would obtain like this way. So this is the, if you plug into this H naught into over there, one will get this one. So therefore, Hubble constant square is governed by this how to say contents of the universe. So energy density, and then cosmological constant, and then corresponding K. So I just restore G and C for the sake of the anyway. Fine. So that's the Hubble Lemaître law. And then I think you guys are already familiar with. And then we can solve. So let's see. So here I call it equation 1, equation 2. Equation 2 is something like a 2 minus 1/2 1 is equal to this one. And then the other thing one can do is that the so ddt of 1, equation 1, and compare with 2, and get rid of the second derivative. Remove a double dot. Then what you get is the following equation: rho dot plus 3 a dot over a, and p plus rho plus p is equal to 0, and this is equivalent to conservation of energy, momentum tensor. Okay, you get this one. So that's what you get is the case, and then what we can do is number 1, 2, 3. So the number 3. And then number 4 is the state equation. So this is state equation. So number 4, with this one can just obtain the solution of Einstein equation. So unknown is what? So A and rho and P. What else are unknown? Those are the
Lambda.
yeah, kind of lambda. Yeah, lambda, maybe lambda. It depends on lambda. Okay, whatever. Okay, lambda. So one can solve if you solve 1, 2, 3, one can obtain the solution of the equation. Okay. And this, if you look at this energy conservation, one can just solve easily. So, for instance, non-relativistic. So this equation states a non-relativistic case p equal to 0. For relativistic, do you know the relation between p and rho for relativistic? P and rho. Huh? Yeah, you're right. So is in fact this one. So this is the relation. Non-relativistic p equal to 0. I mean, usually people just write down, you can just write down p equal to w over rho, and plug that into here, one can solve it. Oh, maybe we can, it's a good exercise, so maybe I can do that. So rho dot plus 3 a dot a, and then rho is like this, p is like this way, so the 1 plus w rho, right, equal to 0. And from here, we'll obtain that the a dot over a is equal to minus rho dot rho. Like this way. Like this way. And you can solve the equation of motion a and rho. For instance, rho is equal to, it depends on rho equal to rho 0, a to the some power. In the case of the, so this, I think it should be minus 3, 1 plus w. Okay. So that's the case. That's the solution. Right? Hopefully I'm not wrong. Yeah, it should be okay. Like this way. Okay. And in the case of relativistic w equal to 0, which means that the rho is proportional to a to the minus cube, rho is proportional to a to the minus 4. Okay. That's the case. W 1/3. So therefore, if you plug that into here, this becomes like this. So this is kind of natural because for the atom it's very natural because I mean, the universe is volume proportional to a cube. Okay, a cube. So therefore, volume is AQ, so therefore the energy density is proportional to A to the minus 3. So that's very natural. And for relativistic one, because of this one, the ratio will be modified slightly. Yes. Okay. Fine. Any question at this moment? I think it's maybe too easy for you, so guys. And then those are maybe already known. Okay. Okay. So, and if you consider so for instance, the thermodynamic first law of thermodynamics in the universe, one can just obtain the following relation: du over dt dt minus sum over a new chemical potential and number density over dt. So these are the first law of thermodynamics in thermodynamics, and then U is energy and V is a volume, and the relation between them, U is equal to rho V. Okay, this is energy and the volume. Okay, and yeah. So if you plug this one into here, what you get is as follows. Actually, B over T rho dot plus 3 A dot over A rho plus P. So that's what you get from here. And ignoring, so number density won't change. If you assume number density will change and plug this one into here, you get this one. Okay. You get this one. And then, so this is equal to 0. So therefore, entropy with universe in the entropy is preserved. Entropy is conserved. Is conserved quantity. Conserved. Okay, so that's what's happening in the universe. In the universe, entropy. So if you assume this here, because I mean we assume that the universe is filled by the perfect fluid, perfect fluid. So which means that the there is no how to say homogeneous. Once you assume homogeneous isotropic, actually there is no friction. So in the since you just change uniformly, the matter field which fill the universe do not make any friction. So therefore, the entropy won't increase. So it's just preserved. But if you, so this is because homogeneous. In fact, I mean, one can show that the if you assume a homogeneous isotropic, the energy momentum tensor is forced to be this perfect fluid. Forced to be perfect. That's also one can derive. You don't need to assume the universe is filled by homogeneous isotropic. That's a perfect fluid. You don't need to assume universe is filled with perfect fluid. I mean, it's a consequence of homogeneous isotropic, in fact. And then due to that, there's no friction between the. So now we go back to the original thing. We have so we have unfortunately I erased, but I will write down again Oscar. So this is the Einstein equation. And now, so assuming that this one, rho is equal to rho 0 a minus q. You can plug into here. Okay? If you plug into here and multiply a square, what you get is as follows. So 1/2 a dot square plus b of a is equal to minus 1/2 k. So one can just write down like this. This is kind of like a Newtonian energy, and where this guy is equal to minus 4 pi rho 0 over 3 1 over a minus lambda over 6 a squared. Okay, so that's what you get. Okay, so that's the case, and then one can just write down what's going to happen, this equation for A. So the potential one, like this way, this is B of A, and this is A. Okay. Okay. So now, if you look at this one, when A is negative, okay? So the A is negative, so the first, when A is very small, so this term is dominant. And we know this one is equal to negative. In total one is negative. So therefore, this is something like this one. Something like this one. The first time something like this one. The second time, when lambda is, if lambda is negative, it becomes like this way. Like this way, okay? So when lambda is negative, this is lambda is negative. So therefore, so the potential will become like this way, something like that. Okay? Like potential B of A become like this way. So therefore, depending whatever value k, so k is something like this one, k is here. So when k is like this way, positive, even if k is positive, it hits the potential wall and it comes back. Okay? So therefore, universe, whatever is start, it somehow reach the maximum and go back to the start shrinking. Universe starts shrinking. The same thing happens when k is negative. The cycle become the smaller. But so in any case, the T and A will be something like this one. Something like this one. T and A become like this way for when lambda goes to negative. Lambda is negative. So on the other hand, lambda is the positive, so it becomes like this way. Maybe I should write that bit bigger. Bigger paraboloid, like this way. And the potential, so like this is lambda, is positive. And potential will become like this way. Like this, okay? So then the behavior is totally different. When k is positive or 0, and I mean, it just goes like this way. Okay?
Which means expands forever.
Yeah. Extend forever. It depends, of course, on initial condition, but suppose initial condition A dot is initial condition is like this way. If you suppose like this way, then it just expands. But the potential, so the difference between potential, so this is kind of like a decelerating. So the expansion is decelerating up to this point, but after that it becomes accelerating. Okay. So therefore, so this the behavior is something like this way. Decelerating. It never gets like this way, like this. Okay, like this way. And then, So the interesting thing is that when k is some particular value, like this way, it hits the maximum point of potential. So from here to here, it takes the how to say, infinite amount of time, in fact, and they just stay like this. This is called Einstein static universe. Einstein static universe. Static universe. Einstein static universe. And then the other case, if it is lower than k is lower, then it hits the potential wall and go back. And the same thing like this. So for this observer, something like this one. So the observer is something like this one. Okay. Yeah. So this, for instance, if you write down this one, it's AS. So this one is the AS. Something like this. So those are the qualitative behavior of how the history of the universe. In any case, yeah. So if you assumed, since at that time people already knew that the A dot is positive. A dot is positive, expanding because of Hubble law. Then, so if you trace back to the time, trace back to what happened in the universe in the past, it inevitably goes to the A is size to be 0. That is called, and nowadays it's a Big Bang theory. Theory. And then at that time it was yeah, big idea. That one is also Einstein is a kind of like hesitate to accept this idea at the beginning. But now there are lots of supporting evidence for this one. Any question at this moment?
But we know that for sure lambda is positive, right?
Yeah.
As we mentioned it.
Yeah.
before.
So A dot is
No,
positive.
lambda is positive.
Lambda is positive. Oh yeah. So lambda is because positive is the found by. I mean, this one is already believed in 1990s. Most of early 1990s. Early 1990s. There are lots of supporting evidence, not solid one, to support this one. Early 1990s, before you guys are born, actually. But in 1998, there's something special. The crucial experiment that happened that clearly mentioned this one. Do you know the experiment? So this is the type 2A supernova. So supernova of type 2A. Type 2A supernova of some star. I don't remember which one. But anyway, so this measurement of supernova in 1998 support this positive cosmological constant in 1998. Yeah. And then okay. I also one thing I need to mention that if you look at this one, so lambda is positive, very small, very small, and then. The universe, the age of the universe is something like this one, right? 1, 2, 3, 4. 1, 2, 3, 4. I think so, as far as I recall, this one. This is the years. Okay, about around roughly this one. But now around the so this is current time. So the current time is somehow the universe starts expanding. So that it just passed this potential, the maximum potential, and it gets bigger and bigger. This difference becomes bigger and bigger. Okay. So around here, we are roughly speaking around here, around this region. It's just we pass this the maximum point of potential, and it starts expanding. And the question is, so after the universe has how to say? I don't know how, this amount of years passed from Big Bang. Somehow our universe starts expanding, and then somehow we live in that area in that period. Okay, in that period. So that's very kind of coincidence why the somehow current universe where we are living is now starts expanding. It's called why now problem. I don't know. As far as I understand, there is no solid answer. Like there are lots of people try to argue answer or I don't know. Anyway, answer. I don't know. Maybe in Chinese like this way. Maybe anthropological principle. Anyway, to try to answer why now problem, but as far as I understand, there's no solid answers to this question. Anyway, so that is called why now problem. Okay. Any question at this moment? Otherwise, I will move on to zeta. Okay. So suppose T min equal to 0. So which means rho is equal to 0 equal to P. And look at the Einstein equation over there. So this one is become like this way. Okay. Lambda equals 3, which I call it 1 over L squared, like this way. So the relation between this 3, okay, anyway, it depends on dimension. This 3 becomes something like, as far as I remember, d minus 1, d minus 2, d, okay. Maybe if you use space-time dimension like this way. It's okay. Divided by 2, something like this. If you go to higher dimension, this coefficient 3 become like replaced by like this way. But anyway, so that's not important. So, okay. And then if you solve this equation, it's very easy to solve. So when A is L of t is L cos t over L when k equal to 1.
So what about 2 dimensions?
E to t over L. What about t 2 dimension? 2 dimension. Coefficient looks strange. That's true. They become divergent. That sounds strange.
2 dimension means one spatial and one time dimension. Right?
Yeah.
Well,
Yeah.
assuming that D is the total dimension.
Yeah, that's possible. Okay, I don't know. Maybe I'm wrong. I don't remember the detail, but something like that as far as I remember. Even 2 dimensions, there must be Einstein equation with cosmological constant, which should make sense. Which should make sense. Yeah. Okay. I don't know, to be honest. Maybe something like then I don't believe. Okay. Anyway, let's not. Okay. Let's not think about some other dimension like this at this moment. There must be a way to derive that. It is sinh t over L when k equal to 1, k equal to minus 1, k equal to 0. Okay. S3, R3, and then R3, hyperbola 3. So locally, for instance, R3 can be replaced by actually something called T3, and so on. But anyway, so the global structure is not important at this moment. So we just only look at the locally like this way. Geometric structure become like this. Fine. So these are solution for the vacuum Einstein equation. So this is the vacuum Einstein equation. Vacuum Einstein equation. Yeah. Okay. So and then
So this is assuming L is real?
yes. So
Lambda
as,
is positive?
yeah, lambda is the here lambda is positive. Yeah, assume lambda is positive. Positive cosmological constant. Yeah, positive. Yeah, thank you very much for pointing out.
Why? Did we just start with that?
Yeah, this is assumption. This is assumption. So this assumption.
We just saw that in order to be the universe is expanding.
So this is called zeta. If it's negative, it's called ADS. Which I'm going to explain from later part. In the later part. And assumption, lambda is the positive assumption, and which is the zeta. Yeah. Okay, and then so to get this metric the upstairs, so let's first consider k equal to 1 case. So to k equal to 1 case, the way to derive this one is that to embed. So it's called embed. ds into R4 5-dimensional Minkowski space, where the metric is something like this one, minus d like this way. And then, yeah, so this ds is the 4-dimensional, ds4 is embedded into the R14, and the embedded surface, the hypersurface is described like this way. This corresponding to the zeta 4. And you just consider induced metric. Induced to obtain the induced metric, what's important is that you just assume this one is equal to something like a sinh tau 1 L, and this guy is the square, and the L square, and the cos tau 1 square, something like this one. Then this will be satisfied. This will be satisfied. Okay, this will satisfy. So the how to say radius square of this spatial part is cos. Will give you cos square. And then for time per, you have a sinh square, and then this will be satisfied, like this way. And then you just assign the other part is spherical one. So x0 is something like a L cos tau 1, how to say, sine or cosine, I don't remember, cosine chi, and then cosine chi, and x1 is something like L d chi tau 1, sine chi, and then whatever spherical coordinate, sine theta, and so on.
First coordinate is a time-like coordinate, right? X to minus 1.
X minus 1 is like a time-like coordinate in R14. R14. So this is time-like coordinate, and these are space-like in 5-dimensional Minkowski space. Yeah. So I just renamed a slightly weird way, because yeah. Anyway. Yeah. X minus 1 is already, I assume this one is sinh tau. Sinh tau 1 and so on. And the rest is just assigned spherically. Okay. Then this induced metric on this surface is something like this one, ds square plus is equal to minus d tau 1 square plus cos, I think over there, tau over L. Like this way. Oh, sorry. It's okay. It was okay. Sorry. No, I got confused. L square, cos square, tau 1. No. It's tau 1 over L. Do I need to introduce tau? Okay, tau 1. Tau 1 is okay. Tau 1. And then d chi square plus chi square d omega 2 square. Okay, so that's what we get. Okay, sorry, I think I made a mistake. This is sine chi, okay. Like this. So this is the kind of S3 metric, but S3 metric. And then you have this metric. Once you set tau 1 to be T over L, so what was it? So this tau 1 to be T over L, that is exactly this guy. The solution for k equal to 1. K equal to 1. Okay, so then everybody likes to draw the figure. I prefer to draw the figure. So you assume this one is x minus 1 direction, x0, and x1 to 3 direction, like this way. Then this, how to say? This hypersurface is something like this one. Do I make a mistake? I think something should be. Oh, okay, it's okay. So when x1 is equal to 0, x minus 1 is equal to 0, so this is just the sphere, right? This part is sphere. Okay? So therefore, x minus 1 is equal to 0, it just become like this way. So this is S3. Since we don't have enough space, it just this direction is suppressed. Okay? So this is x minus 1. But once you increase or turn on the x minus 1, this one becomes essentially just increase the radius of this S3. So therefore, this x minus 1 direction is something like become like this way. I don't know how to draw. Maybe something stupid. Like this way.
Is it S3 or S4? It's 4-dimensional sphere, right?
If 4-dimensional Z 0, 1, 2, 3, 4, 4-dimensional R4, right? So if you forget about this direction, this R4, right?
Yes.
R4 with this surface is S3. S2 is something like x squared plus y squared plus z squared is equal to whatever r squared. That r squared, that is S2, right? But if you increase one more dimension, S3. Okay, and then this direction is x1. So the surface, each spatial surface become like this way. Okay, like this. So this is the surface for the zeta. Okay, and And then one can have the sum. So that's the k equal to 1 case. The question is, what is the other k case? How about the other variable k? So this can be just obtained by the following parameterization, e tau 2 and then x1. So this is e tau 2 chi sine theta cosine phi. And x2 is equal to like this. If you parameterize like this way, it's a tedious. Actually, to derive this one, it's kind of tedious. I realized it took for me like more than 1 hour to derive this one. Actually, the metric is something like this one. In this metric from here. So in this metric here is S square is equal to L square minus d tau 2. This way, and once you set tau 2 is equal to t over L, then you have the t square. Like this way. So that is exactly this k equal to 0 case. K equal to 0 case, like this way. Okay. In fact, so here we have to use this relation. So you have a five variable. But here you have some less variable, tau 2 chi theta phi. But you have to impose this condition. You have to impose this condition to obtain this relation, to obtain this metric in this metric. Actually, this from here to here in this metric is exercise. It's a good exercise. For GR. But I'm not going to do that. It takes a kind of, by hand, it takes a lot of time to derive this one. But instead of showing that, in fact, so this x1, x1, so this is constant surface. T is called constant surface. So this is the, how to say? T is called constant surface. So in the case of k equal to 1 case, this S3 is t equal to constant. T equal to constant. Or t equal to constant means tau 1 is constant. Tau 1 is constant. Well, maybe I call it tau 1 is constant. Tau 1 is constant. But tau 2 is equal to constant. Means that so x minus 1 plus x0 is constant, okay? So therefore, x minus 1 and x0 is constant means that the surface is really become like this way. So it becomes constant tau 2 surface, something like this way. So this is tau 2 is constant, something like this. So this is kind of spatial slice in this surface. So these are tau 2 is constant surface. And then here at the end it become like this way. Anyway. Like this way, at the end. So those are the k equal to 0 case. Okay. So k equals 0 case, this part is flat. This part is flat. Okay. Anyway, so those are tau 2 equal to 0 case. And then let's move to the k equal to -1 case. The last case can be obtained the following from the static chart. And then like this way. So if you take this kind of coordinate, the corresponding, sorry, I made a mistake. Sorry, this is not the correct one. Sorry. So this is later. Sorry. K equal to 1 is different. Sorry. Sorry. So x minus 1 is equal to L sin tau 2 cos chi, and x0 is L cos tau 3, and x1 is equal to L tau 3 sin chi sine . Arbitrary?
Yeah. To satisfy the equation, right?
To satisfy this equation.
Yes.
Yeah, and then to satisfy this equation, but we need to get the correct metric. So to get this, this metric, induced metric, to get the induced metric, what we need is that the what was it? So tau 3 is constant case is now, tau 3 constant means x0 is constant. Tau 3 is constant means x0 is constant, which means something like this way. So these are special circles. Okay, so these are the tau 3 is constant. And in this metric is exactly this guy. Exactly ds square is equal to minus dt square plus L square sin square L. Like this way.
Is there two components? Shouldn't we draw the
Yeah.
second component on the lower?
Good point. I mean, it has also lower component. You can have this as a lower component. It depends on how you choose. Yeah, since cos tau 3 is the positive, so I just pick a positive one. But you can put the negative sign but you can get the
It's
same.
about the sign of the x0. It's about the sign of x1, x minus 1.
Yeah, you're right. So it depends on the sign of the. How does the sin is something like a e to the tau 3 minus e to the minus over 2 or something like that, right?
Yes.
So when tau 3 is negative, it can be negative, right?
Yes.
Right?
yes, I do.
So therefore, this surface is tau 3 is the, tau 3 is negative, and this is constant is positive. So that's the case. So those are special circle for this coordinate, this coordinate. This is k is -1. K is -1. So therefore, depending on take a slice of this hyperboloid of inside a Minkowski space, you can have a different induced metric. And corresponding one is k1, k equal to 1, k equal to 0, and k equal to -1. So that's how you obtain this solution of the Einstein equation. So Einstein equation. And then the one I wrote here is called static coordinate. And static coordinate. And then this metric is the given by ds squared is equal to -1 dt squared. The omega 2 squared, like this one. And then r. So here, to well-define r should be less than L. So this is the condition you have to take. R equal to 0, radial coordinate become null. Radial coordinate null. So then r equal to the r equal to greater than 0. This becomes time-like coordinate, and this becomes the special like coordinate. That's the case. But anyway, so we assume this one is the valid in this range. So this is called static coordinate for the zeta space. Okay, so that's what we have encountered. And then, so in our universe, I already erased some portion of it. Yeah. So in our universe, we already encounter lambda is positive. So we know the lambda is positive, and our universe is accelerating. So which means that we move on to this dot zeta regime. Yeah. And then in our universe, that's the case. Okay. Then let's have a break for time being.
This characterization doesn't cover the whole.
Doesn't cover whole.
So what's the deal? Should we a couple of charts to cover the whole thing, or only this region is?
So it only covers some part of the To get this kind of metric, we can just obtain it by looking at some special some slices of this hyperboloid, but it only covers some part of the space.
Can we cover more?
Can we cover?
Well, obviously we can do it. It's not minus L.
Yeah.
And
This
cover that region, but
Yeah.
there's still the.
In the middle.
Yeah, it's not between L
Yeah.
and minus L.
That's true.
How do we?
How do we?
It seems the topology of these space slices is kind of different
That's true.
in those regions.
That's true.
It does not happen for k equals 0 when it seems a bit well. Oh, it's the same thing. On the breadboard, right?
Yeah.
We have
This is the only valid for.
cosine, hypercosine of t over L.
Yeah.
So again, it only covers, it's not greater than square root of L squared minus R squared.
Yes, that's true.
So
So
we need to choose different, another chart, like a couple of charts. But here it at least covers like x naught can go to 0 when R is but here it can't. That's looks like we need another chart for
Yes, yes, yes.
yeah, I think what I want to say is, I mean, this is how we obtain by in this metric for k equal to 1 and 0 and minus 1. And then I don't know. I mean, for T3, in this case, I mean, you just start with something like a. How does it work?
yeah, it covers only those yellow slices.
Yeah.
What about the yellow slices in the middle?
It's like a
You mean like this way? You like it this way?
Yeah.
That's impossible. Somehow.
Well, with this coordinate chart, yes, but
Yeah.
if we choose a different coordinate chart,
Yeah, that's true.
then-
That's true. That's true.
Cosmological constant in 2D, since the 2D gravity is true, 2D Einstein gravity is true.
So it's only lambda equal to 0?
So what you write for the alpha is correct.
Okay.
A minus
Well, it's,
Yeah.
it's correct.
1 divided by 2 or something like that.
yeah, L squared.
Yeah.
D equals to is 0.
Yeah.
It's integral Einstein Hilbert action.
Yeah.
Is all
Oral
the
characteristic,
parts-
yeah.
So the 2D gravity is true in dynamics.
Okay. Yeah, somehow lambda needs to be 0 for d equal to
2, right?
d equal to lambda must be 0.
So in general, why do we need the dosector, anti-dosector, or what is the use of? It's like seems like a submanifold of 5-dimensional Minkowski, right?
Yes.
So
That's
what is our aim to introduce it? So we just define the 5-dimensional Minkowski, and
Yeah.
We got some equation.
yeah.
And why are we doing this?
No, what I meant is that that's how we can understand that the how to say accelerating universe when k equal to how to say positive case. I mean accelerating S3 is something like just behaving like this way. If you embed in 5D Minkowski space, it's easy to understand. It's easier to understand the how does the S3 just moving they become bigger and bigger. But in the case of the
And how you choose the parameterization? For example, you choose x minus 1 plus x 0 is this, right?
Yeah.
You can do anything else also. Why you choose this one?
To get this metric. To get this metric. Out of this minus dx minus 1 squared plus dx 0 squared plus plus dx. So from here in this metric is this one. So this is exactly going to k equals 0 case. But this is only possible when you do this kind of slicing.
So you choose this in order to get this,
Yeah, yeah.
or you choose this and you get this, or which one?
I choose this one to get this one.
And why you choose specifically like this? My question.
Why I choose?
Specifically like this. Can you make anything else? For example,
No,
let's say-
no. Then you won't get this equation. You won't get this metric.
You mean it should be this flat?
Yeah, and also this prefactor needs to be like this way.
Mhm.
Needs to be like this. That uniquely tell you that this is the only canonical choice, only choice you can make.
Okay. It's like a scale factor here
Yeah,
and flat.
yeah, flat.
Mhm.
Let me get something. Okay. So let's resume. So now we talk about the lambda is negative. Lambda is negative. Then you should put the minus sign. You should put the minus sign. So then so you realize that the right hand side needs to be negative, but left hand side also needs to be negative, but this is positive quantity, so therefore k has to be negative. Okay? So therefore this kind of solution is not allowed. Not allowed. So k needs to be negative. And then this should be become sine. This becomes sine instead of sine t over L. Okay. So this solution does not exist when lambda goes to 0. And this is called anti-dosita. Anti-dosita. Oops. So anti-dosita. And people just write down like this way. ADS4. Okay, so that's since this is not the solution for that describes our real universe. We know that our real universe lambda is positive, And we are now experiencing de Sitter phase, but here this is not real. It does not describe a real universe. But the one thing we encounter is that the Reisman Nordstrom extremal, Reisman Nordstrom near horizon geometry. Behaves like it behaves like a ADS2 cross S2 near horizon. Okay. So that's the one thing which tells us that it's worth thinking about the anti-de Sitter space. And then many of you already heard of a so-called ADS-CFT correspondence that will describe something very important about the quantum gravity, and so therefore anti-de Sitter space does not describe our real universe, but it's important to study. Okay, to get this metric, so again we consider 5-dimensional space, but we embed instead of 1,4, we embed like this, which means that the metric of this space is something like this way. You have a minus, so this one is -1, -1, +1, +1, +1. X0 square plus x1 square plus x2 square plus x3 square, like this way. Sorry, d, I forgot to put the d. d and then you just consider like this way. Like this way. Like this way. Then, so the metric we can consider is okay. So we can consider the following metrics. So here we just assume that the metric we can consider is what's going on here. I think I made a mistake in the coordinate. Oh, I see. I think my coordinate is not correct. Huh? Sorry, I got confused. So what we want is the coordinate metric, induced metric, something like this one. Minus dt squared plus the a is like this way, L sine square t over L, and then d chi square plus the sinh square chi d omega 2 square. That's what we want. To get this one, I understand. Okay, I understand. It's okay. So what I wrote is correct, actually. L sine t over L, and then cos chi x0 is L cos t over L, and x1 is L sine t over L, x2, x3. So it's the same. It's the same, and then sine theta, sine. like this. Okay. So then the induced metric like this way. So you can see that they satisfy this equation. They satisfy this equation as follows. So if you just multiply, so x minus 1, x1, so if you first evaluate this one. So what would you get? What would you get if you evaluate this one?
First one is 0, right? X0.
X minus 1. Yeah, this one is equal to L squared sine square T over L squared. Minus. Okay, you're right. Okay, and then if you add the minus x0 square, you get the minus L square cos square T over L. So therefore, this is minus L square. Okay. Do you agree with me? Okay. So the first, this part it will give you minus L square sine square T over L, and so on. And the induced metric, if you do the honest calculation, you will get this one. Okay. You get this one. So this is the anti-zeta space for solution. So therefore, often people just write down like this way. Maybe I can erase already this one. So here, so this is the hypersurface we consider. So therefore, if you write down this one is x minus 1 direction, this is x1 direction, and this is equal to x0. 1, 2, 3 direction. So once you set x0 and then x1, 2, 3 is equal to 0. So if you set everything 0, this will give you this S1 circle. So therefore, in the middle you have the S1 circle. And then maybe a little bit smaller. This is S1. And then once you turn on x1, 2, 3 direction, it's something that behave like this way. It behave like this way. Sorry, I think my drawing's not beautiful. Like this way. So here in the smallest circle one can obtain is the x1, 2, 3 equal to 0. Okay. x1, 2, 3 is equal. And if you turn on that, so if you just move this one here, S1 radius become bigger and bigger. Okay. So those are the hypersurface. And we just consider some, t equal to constant is something like x naught is constant. Okay, x naught is constant is so x naught is constant is something like I don't know, it's hard to draw, but anyway, I don't know, something like this one. Like x naught is something constant, is something like this. So these are x naught is equal to constant. It's exactly the t equal to constant. T equal to constant. T equals to constant slices. Sorry, t over there. Okay. Yes. So those are the slices one can consider. Okay, in the case of ADSL, ADS, there are kind of many coordinates one can consider.
I'm sorry, here L x naught is bounded between minus L and L.
That's true.
And so in this picture, we don't have all possible yellow lines, or what?
So here it's a x naught is kind of bounded because I mean here it's just circle, right? It's circle, it's bounded kind of. So the here cos, yeah, of course here cos is equal to -1 to 1, but here also here it's circle. So this x1, how to say, x naught is equal constant is also bounded.
So it's like the complement to the picture that we had before.
Yeah, yeah, yeah.
We only could have these two separated regions. Now we only have this.
Yes, yes.
Okay, and the.
Yes. But here the metric is different. Okay, and we can have different kind of like coordinate. One is called static, the static coordinate, static or global coordinate. So which is something like this one. Sorry, 1, 2, 3. Okay, then induced metric is something like a very, very similar to what we had before, but here it's much more natural because there's no restriction on the R. Because here R is can be just positive number, dt square. Okay, something like this. Okay, and then we can set this R to be something like how to say cos. Yeah, L sin rho. Then this part becomes cos square rho, and this part is 1 over sorry. This cos square rho, and I need to change a variable. Okay, special part. The special part will become something like a d rho square plus L square sin square rho d omega 2 square. Okay, something like this. So one can just write down like this way. So it's written the very, very how to say symmetrical manner. It's kind of like a spherical coordinate of an ADS space. Okay. So the metric is something, maybe I can write down again. X squared is equal to minus cos square rho plus d rho square, dt square plus sin square rho d omegas. Something like that. Fine. So that's the coordinate we can just see the fine. So in this case, so now T1 takes the value inside of here. So therefore, T1 is something like it just wraps. So it just wraps many times like this way. Okay, it just so as you know. What's that? So if you look at this one, so it's just some covering of this space. Covering of space means that the so since we have the R goes to S1 divided by Z2, Z. So if you just have R, and if you just separate like this, identified by z, so you get the S1, sorry, S1. So it's the same thing happening in this coordinate. So t just wrapped this S1 coordinate infinite many times, okay? Like infinite many times. So therefore, it's just an infinite many cover of this whatever kind of hyperboloid inside of R23. So therefore, this is called global coordinate. Global coordinate. Okay. Now another coordinate people just familiar with is that the so-called Poincare coordinate. So the Poincare coordinate. So here we just set the R is equal to x minus 1 plus x3. And this x vector is the x1. Like this way. And like this. Okay, so then, and also I set the y to be minus x plus x3. So then the metric become like this. I already raised ds square is something like a dr dy plus dx square, like this way. So here, this guy is something like a dx0 minus square plus dx1 square plus dx2 square, like this way. Okay, or one can just write down the metric is something like a L over L square, R square, dr square plus dx minus like this way. So this is one way to write down the metric. So in the second, so from here to here, so from here to here, one has to use a relation that the yr is equal to minus L square minus x square. So if you use this relation, one can just write down that this equation is equal to this x, like this way. So one can just write down like this. Then, if you just introduce the coordinate something like a y, like this way, then which is the r times x. If you like this, if you introduce this coordinate, and then what we have is something like this one. This is equal to ds square is equal to L square over R square. So this part is the same, but this part, because of the introducing R coordinate, one can just replace by R square dy square, like this way. So it's a very simple form. Okay, so this is called Poincare metric. Okay. So this is called Poincare metric. So the reason why it's called Poincare metric, maybe I can erase that. I think, yeah. For instance, if you do the following transformation, I think I don't include a dr square here, plus dr square, like this way. So, and if you change this kind of like one over, let's see, how do you write that? L squared W. Let's call, if you do this kind of transformation, this metric will become like this way. L square omega square d omega square plus dy square. Okay. Dy square like this way. If you do the change of variable like this way, and this is the, I don't know, it's a have you ever heard of this upper half plane? So this H, and then the metric we consider is the dx. So H the upper half plane x and y, and the metric we consider is something like x squared plus y squared divided by dxy dy squared divided by y squared up to some number. So this one is the geodesic is something like a half, how to say, the circle, like this way, or a line like this way. So these are geodesics for upper half plane. Yeah. Upper half plane. So this is exactly the similar, but in this case, y is something like y0 or y1. In this case, y2, I think, y2, yeah. y2, because of this relation, is that the here metric is something like dy0 square plus dy1 square plus dy2 square. Here actually indeed. So there is some negative sign instead of like a Poincare metric. But in any case, what we encounter is that the so here I just a bit more. We can just consider the similar consideration. So this is the w direction. This is w direction, and say this one is the y0 and y12, 0, 1, 2 direction. So if you consider like this way, so if you have an upper half plane, so this is w equal to 0 plane, and you consider this direction like this. And then the geodesics again become like a, how to say, like this way, like this way. Yeah, geodesics is become like this way in the y12 direction. But here, once you set the how to say, w is equal constant plane, constant plane, where the constant plane is like this way. So then this one is behave like a Minkowski, 1, 2. So it's a Minkowski space like this way. But with a scale, something like a scale is have 1 over w squared. 1 over w squared. So therefore, which means that the length around here is something like a length around at the bottom. It becomes really scaling if you go to like this. Anyway. Anyway, so that is the, in the case of eddy CFT correspondence, this is called scaling transformation. So the length here around here is something like around here is length like this. Anyway, 1 over w square scaling. So therefore, it's called renormalization group law and so on. Anyway, so that's why it's called Poincare coordinate. I used to anyway. So a bit detour, but it's important to you never. So it's the upper half plane. So this upper half plane. So this dx squared plus dy squared divided by y squared. So these are metric. But here you can just consider this is the origin, and this unit disk circle. This is called. And then you have a circle around here. And it's a bigger circle. One can just roll. Sorry, I fell. I failed. Anyway, so the bigger circle one can just consider like this way. So upper half plane. Once you just reverse upper half, how to say, inverse with respect to yellow metric, upper half plane can just squeeze into this disk. This disk for unit circle. Okay, so this is called Poincare disk. Poincare disk, and whose metric is something like this way. What was that? Dx squared plus dy squared divided by, no. 1 minus x squared plus y squared. Something like this one. So it's a unit disk. R equal to 1. But geodesic is something like it's called how to say? Paraboloid. Yeah, I think it's anyway. So geodesic is something like that. Anyway, so it's this disk is the model for Escher. So you might have seen like there's some fish and so on, like a tiled on the one disk, and then once you go to the boundary, it's the fish become very very tiny. That's the Escher's disk, but those are the model for this Poincare disk. Anyway, so those are the upper half plane and the Poincare disk as a Riemannian manifold. It's the same. So we can do the same trick for this, even this with this ADS space. One can just squeeze this upper half plane into some kind of ball in the appropriate higher dimensional plane by using same trick. So that's why, anyway, that's how we can just do that. And so on. Yeah. That's why, and then so that's why it's called Poincare coordinate. It's called Poincare coordinate. Any question at this moment?
Yeah. So this is kind of almost like H4. Is there a ball model for this H4 with this on this Lorentz signature on the slices?
So usually what people do is only looking at the how to say space part or space part. Space part is put into the ball, so that I can do that. So this space part is this part, right? So this plane, right? This plane is a space plane, right? And this space plane can just put into the disk. And the y coordinate is just treated as a time. People just write down like this way. So y0 is this direction, but this space coordinate is h3 can be put into the ball. So this is kind of like a d3, and then just y0 coordinate is something like this. So people in ADS CFT community, people use this kind of diagram to describe a ADS space.
So it's like R times H3,
but
not H4.
Yeah, that's all right. Yeah. People treat like y0 is a time coordinate, and here is that you have a Poincare ball you have as a space slice. Any other questions? So this can be generalized to the again. So here, this y vector is something like a y0 plus dy1 plus dy2, and appropriate squared. But we can just continue to the dy whatever square d minus 2 direction. So then this corresponding to so-called ADS d-dimensional ADS space. So that's how you generalize to the high dimension. Okay. And then, so once you consider the ADS, this kind of space, n plus 1, then this one is described by like this way. see, n plus 1 means what? Let's see. N minus 1 square is equal to minus L square. Okay, say L square. And this hypersurface, so there is a SO2 will rotate this part, and this part is SO n minus 1 will rotate like this. And then combine together. I think I made a mistake somewhere. Sorry, I think this should be n in that case. Yeah. 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 So combine together SO2, n will acts on it is Sn plus 1. Oh, space. So this is a symmetry, geometric symmetry on it is n plus 1 space. Okay. And this guy, so if you define the eta, the Lie algebra of this, it's a rotation. It's a rotation of this it is space, and if you define the eta, how to say, whatever, nm or mn is something like a -1, -1, +1, +1. So this is there is an n of them. Then the Lie algebra satisfies as follows. J mn J pq J. Like this way. So this is the algebra of SO 2, n. So it's just it's the same. I mean, if you change the J eta as the -1, +1, +1, then it's just a Lorentz algebra. You encounter in QFT, and if you just make it everything plus, it's just a Lie algebra of SON. So orthogonal, special orthogonal. It's just the change of eta. It just go from this ordinary rotational group to this Minkowski or like a generalized Minkowski rotational symmetry. Okay, and then we can just decompose as follows. We treat, so we have like a -1, 0, 1, 2, n minus 1, n direction. And we treat this one is a Minkowski, n-dimensional Minkowski space. This is R1, n minus 1 Minkowski space, where the SO1, n axon. And somehow we treat this direction as some kind of light component. And so therefore, I just define the x plus minus is equal to plus minus like this. Okay. Then one can just call it. One can call it. Okay. One can call it this. D is 1/2 J plus minus. So I just call it that this one is D, and the P mu is equal to J plus mu. Then K mu is equal to J minus mu, and the M mu J mu mu. So that's where mu and nu are 0 to n minus 1 direction. Okay? N minus 1 direction. I just call it this one. Then it turns out that these are the so-called, they satisfy so-called component algebra of R1 comma n minus 1. So this one is just a Minkowski or Lorentz boost, or whatever you call it, Lorentzian rotation. And this is translation. And this is called dilatation. And this one is corresponding to so-called special component transformation. And then just use this relation. One can write down the algebra or computational relation for these generated. So I only just write down the list of some important. I just only write down the important relation. For instance, we have the D and a P mu is like a P mu, and D and K mu is behave like a minus K mu, something like this one. Okay, and then M mu nu P rho is something like it behaves like a vector A mu rho P mu. Like this. And then K also behaves same way. Like this way. So P and K kind of like play very similar role. But the charge with respect to the dilatation is this +1 and -1. +1 and -1. And also the P mu and K nu computational relation. And everything can be derived from here. It's something like a -2 8 mu nu like this. Okay. So these are indeed it's called the component algebra. So this is a Lorentz symmetry. So this is Lorentz symmetry plus the translation is called Poincare symmetry. But if you add this special component transformation, automatically will give you D, automatically because of this computation relation. That will call the so-called component symmetry in the R1,2. R1, n. So therefore, the reason ADS n plus 1 will give you CFT n dimension. So there is some relation in terms of symmetry between these two. So these are some like a very naive evidence for ADS CFT correspondence. So. Yeah. So in the case of the so maybe I should mention the CFT, so that so the R1, n minus 1. So the origin here, and then so there's some circle here. So the D is the some kind of dilatation. It's called dilatation. It's just scaling transformation. It just generates the circle. It just generates scaling transformation. So therefore D is something like a x mu partial x mu, corresponding this way. On the other hand, special component transformation is a bit more involved. So if you start with this point x, you just inverse with respect to unit circle. So if you just consider this a unit circle, if you consider R equal to unit circle, you just map to the opposite one, so which is x mu divided by x squared, like this one. And plus some vector, so this is a finite one, so this x mu over x squared plus f mu is like this way. And then just take an inverse. So let's go x prime. So take inverse, which is x prime mu divided by x prime squared. Okay. So those are called special conformal transformation. And if you consider infinitesimal version of this one, so k mu is something I don't remember. K mu is something very complicated. Something like this one. Let's see. Something like x mu, x dot mu, some number, some quotient are equal. I don't remember the detail. Something like this. And they obey this kind of commutation relation. So those are the some evidence for the symmetry between. Yeah. Anyway, so in any case, so we know that this area space have a SO2, n symmetry, and somehow, in the case of the conformal field theory, also have a same symmetry, even though the dimension is one dimensional less. So that's what's really happening. That's one evidence for showing the naive evidence for LS-CFT correspondence. Any question at this moment? Okay. Otherwise, so kind of time is limited. So, but. So in terms of generator, so this is so order. So let's see, -1 direction, and the n direction, and 0 direction, and 1, 2, 3, till n-1 direction. So these are like this way. -1 n, and then 0, 1, 2, 3, and so on. Okay, so the in terms of metric, so this is equal to j mn. So in the symmetric, so here you have a m mu nu, and you have a d here. The rotation is coming here, and since it has to be anti-symmetric, it has to be d. And here we have the p mu. As far as we have a plus, so I don't remember plus or minus. So k mu divided by 2 here. And then in this entry, you have a p mu minus k mu divided by 2. Okay. These are entry for this, the big SO2n to n. And then it has to be, everything should be anti-symmetric. So this one is minus of this one. This one is minus of here. Minus of this, and so on. Anyway, so those are generated in terms of the conformal symmetry. Okay. Okay. Unfortunately, time is. I don't have so much time to explain. So now we have exhausted so far the famous exact solution, both the black hole. So black hole. So that's so far what we consider is the Schwarzschild, rational Northstone, and the Newman, and so on. And for universe, we saw that the FL, RW, to zeta and ADS. Those are exact solutions we consider so far. Okay. And here, so everything somehow has, consequently has singularity in space-time. And here it predicts in the past the universe shrinks to 0. So somehow, if you solve the Einstein equation, so you inevitably encounter this singularity and so on. So the first person who tried to address this issue, many people try to address this issue. I mean, as I mentioned, the first one is Oppenheimer, Snyder, Snyder mentioned the black hole and so on. And then the first person tried to explore Ray Chatterjee. He's the actually Indian physicist. Actually, he's a teacher of Ashok Sen. Anyway, he's famous string theorist. He's a supervisor of Ashok Sen. He tried to understand what's going to happen. So, and nowadays he derives so-called nowadays called Ray Chatterjee equation. And from here, people just Penrose and Hawking show that the Penrose and Hawking show that the so-called singularity theorem. Derived singularity theorem in space-time, inevitably, if you solve the Einstein equation, inevitably encounter the singularity of space-time. So this one is the next target of the coming in the. So this exact solution is the first part of the discourse. In middle part, our goal is to try to derive singularity theorem by using the Ray Chatterjee equation. But before then, we talk about the so-called Killing horizon. Killing horizon, and also like a surface gravity. And so on. And then also there's a zero thermodynamics role. Zero thermodynamics mentioned that if you put the things for a long time, it becomes equilibrium. In the case of the black hole, is that if you just put for stationary black hole, the surface gravity at the horizon is a constant. So that's the zeroth law of the black hole. So we will derive zeroth law of the black hole thermodynamics from now on. And then eventually we'll move to singularity theorem. And also we talk about so-called ADM energy. And also so-called positive energy theorem. The famously proven by Shaw and Yao. And later, it's Witten gives some elegant derivation for positive energy theorem. Anyway, so one can just from ADHM energy is that if you just do some integral at the infinity, space shell infinity of the black hole, one can just measure mass and also angular momentum and charge and so on. So that's ADHM. So those are the middle part of this course, the goal of this course. And after this one, we will move on to so if you just solve this, if you just prepare the Ray Chatterjee equation and then the Killing horizon, it's almost the black hole thermodynamics will automatically follow, actually. And if you look at I don't need to write down to be honest, I don't need to write down the lecture note for black hole thermodynamics because, I mean, if you look at this Badin and Carter, Hawking, this paper is a textbook, really. I mean, it's just a perfectly written, and then, I mean, seriously, it's just copy and paste of this paper is enough for black hole thermodynamics anyway. Anyway, so if you just download this paper, just read it. That's the best way to learn black hole thermodynamics. Read it. It's called textbook. It's a beautiful paper. Anyway, so that's what we're going to learn. After that, the last part of lecture is this QFT on the in-curved spacetime. So that's the goal. And I don't think I have a time to talk. It's better not to talk about the. So I'll start killing horizon next time, and move on to Raychaudhuri equation. So let's stop here today. If you have a question, just tell me. Yeah. So you need to drop the.
Kind of. I mean, I have so many courses that
Yeah.
we're going, and
Yeah.
most of November I'll be going.
Okay.